Hey folks, today I'm going to just walk you through a little bit about wave functions and how we use them to describe the wave-like properties of electrons. This is going to summarize some of the stuff that's in the introductory study guide that some of you have emailed me about, and I thought I'd just record some answers here for everybody. So our journey into wave functions really has to begin with the concept of wave-particle duality. And that is that the electron has both wave-like and particle-like properties. Which is weird, of course, because we don't experience anything like this on the macroscopic scale. So we'll begin with the Debroid Postulate. And the study guide explains how you derive it. I'm not necessarily interested that you know that, but you do need to know what the Debroid hypothesis or the Debroid postulate is. And that is that particles with mass m and velocity v have a wavelength that equals Planck's constant divided by mass times velocity, and based on the physics definition that momentum equals mass times velocity, the wavelength of a particle is equal to Planck's constant divided by momentum. And this is going to be important as we think about wave functions, just that there's a fundamental relationship between a particle's momentum and its wavelength. All right. Now remember that the mass of the electron is very small. And so, of course, the smaller the denominator here, the larger the wavelength is going to be. For you and I, our mass and momentum is large enough such that our wavelength is infinitesimally small and doesn't matter. But if you're an electron and you have a very small mass, suddenly your wavelength is fairly large relative to the size of the electron and becomes important to think about. Okay, so that's step one. Step two is to try to understand what a wave function is. A wave function is just exactly what it sounds like, a mathematical function that describes the behavior of a wave. And we call the behavior of a wave its evolution, how it changes in space and time. Okay. And the wave function for an electron around a positively charged nucleus, the allowed wave functions take the familiar form of the s and the p orbitals, but to understand some of the information that you can get from a wave function about the electron, it's useful to take a step back and just use a generic wave function, one that just describes a generic wave, not necessarily an electron. So I'm going to use the simple wave function that's given in the introductory study guide. A Greek symbol for the wave function that we're going to use is the Greek letter psi. And if you have a hard time remembering that Greek letter is named psi, just think of Raphael, the Teenage Mutant Ninja Turtle, and how he had a weapon which was called a psi, and it looks kind of like the Greek letter psi. Turtle power. Anyway, sorry. So what I'm going to write now is an equation for a cosine wave. And that is the number E raised to the power of I times kx minus omega t. Oh, that looks awful. Don't worry, it's not as awful as that. There's a relationship in math that tells you e raised to the I theta is equal to cosine theta plus I times the sine of theta. So cosine of kx minus omega t plus the imaginary unit times sine of omega t, where x is distance and t is time. E is the exponential number, this 2.718 and so on. I is what we're going to call the imaginary unit, or in other words, the square root of -1. I don't expect you to know or derive how this that I'm circling here, e to the I theta, is equal to this over here on the right-hand side. That's a mathematical identity. You can look it up, and there are proofs of it on YouTube if you want to look at it. I only barely understand them, but just because you don't understand the proof doesn't mean you can't use the outcome of that proof. And so we're going to accept this as a mathematical identity, as true. All right? Well, what about this constant k? K is a constant that's going to tell us the number of wave cycles in radians that we go through per unit distance. So as an example, if we wanted to talk about how many wave cycles we go through in one wavelength, that would be 2 pi radians. That's one time around from the start of the wave to the finish of a wave. 2 pi radians in one wavelength. And in fact, you can define k as being 2 pi over the wavelength. All right. What about omega? Omega is radial frequency. This is frequency in terms of radians. Regular frequency, F, is in units of dimensionless cycles per second, or hertz. Radial frequency is expressed in radians per second. So if you want to convert regular frequency to radial frequency, you come up with the conclusion that omega is 2 pi radians times the frequency. All right? So let's evaluate the wave function at various distances x and at various times t. Let's begin in an easy way by saying that time t is going to equal 0. Okay? Let's let the distance x be 0, shall we? That's fun. All right, so cosine of k times 0 minus omega times 0 plus I sine k times 0 minus omega times 0. Well, what does that equal? Cosine of 0 plus I sine 0. The cosine of 0 is 1. The sine of 0 is 0, so you end up with 1 plus 0 times I, which just equals 1. All right, So if we wanted to draw a graph of our wave, we would have amplitude on this y-axis, and then distance on the x-axis. And we would say based on our analysis here, at distance 0, our amplitude should be equal to 1. So, yeah, for fun, let's put a little red dot there. Okay, now let's do the same thing. Let's say that our distance is 1/4 of the wavelength. All right, so a wave function should equal cosine of, now remember that k is equal to 2 pi radians divided by the wavelength. And then our distance is wavelength divided by 4 minus omega times time equals 0 plus I sine of 2 pi divided by wavelength times wavelength divided by 4 minus omega times 0. That's equal to the cosine of pi halves plus I times sine of pi halves. All right, that's 90 degrees. What's the cosine of 90 degrees? Okay, the cosine of 90 degrees is 0. What's the sine of 90 degrees? The sine of 90 degrees is 1. So at 1/4 of a wavelength, the real portion of our amplitude is 0, whereas the imaginary portion of our amplitude is 1 times I. So you can think of this imaginary portion as where the amplitude goes when it goes to 0. So let's let let's say that this distance here is 1/4 of a wavelength. So at this point, the real portion of our amplitude, the one that we can measure, is 0. Okay? Now let's try pi halves. Or let's try, let's try 1/2 of a wavelength. So the wave function, if we evaluate that, should be 2 pi over wavelength times pi divided by 2 minus, remember, time is still 0, plus I sine 2 pi times the 2 pi over the wavelength times wavelength divided by 2 minus omega times 0. That's going to equal cosine of pi plus I times sine of pi. What's the cosine of pi? Well, that's -1. What's the sine of pi? That's 0 again. So if we go out to 1/2 of a wavelength, we'd find that our amplitude is -1. Okay, and so we could go on. We will find, for example, that if wavelength equals 3/4 pi, that the wave function equals cosine of 3 pi halves plus I times the sine of 3 pi halves. And the cosine of 3 pi halves is 0. whereas the sine of 3 pi halves is -1. So at 3/4 of a wavelength, the real portion of our wave function is back to 0. And then 1, 2, 3, 4, if you get out to 1 full wavelength, you are cosine of 2 pi plus I times sine of 2 pi radians, and that is back to 1. Okay, so we have been through one wavelength of the wave. The wave function has a real portion and an imaginary portion. The real portion is the thing you can measure. The imaginary portion you can think of as where the amplitude goes when it goes to 0. But you will see in just a moment that this imaginary term is actually what allows the wave to move over time. Okay, so we can continue in increments of 5/4 of a wavelength, 3/2 of a wavelength, and so on. And we'll see that our wave continues to vary in this fashion. All right. All right, that may be a little bit better than what I would have drawn in class. Okay. Well, now we've got a little bit of work to do. Let's go ahead and try to reproduce this table, but let's let the time be a little bit different, shall we? All right, remember what frequency is. Frequency is number of dimensionless cycles, wave cycles, per unit time. So if we want to know how much time per wave cycle, we would do 1 over the frequency. So if the time per wave cycle is 1 over the frequency, the time to be halfway through a wave cycle would actually be 1 divided by 2 times the frequency. Okay. So we're going to now let t equals 1 over 2f, and we're going to remember that omega equals 2 pi times f, or f equals omega divided by 2 pi. So at time equals 1 over 2f, that'll be the same as 1 over 2 times omega divided by 2 pi. Or in other words, time equals pi divided by omega. That's how much time we're going to let elapse. Now let's do the same thing with distance and wave function and see how that affects the value of our wave function. So at distance equals 0, but time equals pi over omega, the wave function is equal to cosine of k times 0 minus omega times pi over omega plus I sine of k times 0 minus omega times I, or times pi divided by omega, or cosine of minus pi plus I sine of minus pi. What is the cosine of minus pi? Minus pi is the same as pi, -1 plus I sine of pi, which is 0. So that tells us that after we've let pi over omega seconds lapse, at x equals 0, our amplitude is actually -1. Okay. What about at wavelength equals, at distance equals 1/4 wavelength? Well, cosine of 2 pi over wavelength times wavelength divided by 4 minus omega times pi over omega plus I sine of 2 pi over wavelength times wavelength divided by 4 minus omega times pi over omega. What's all that going to equal? Cosine of pi halves minus pi plus I sine of pi halves minus pi. What's pi halves minus pi? That's minus cosine of minus pi halves plus I times sine of minus pi halves. Minus pi halves is the same as 3 pi halves, so the cosine of minus pi halves is 0. And the sine of minus pi halves is -1. So the real portion of our amplitude at time equals pi over omega should be 0. All right. And using the same kind of reasoning, we can demonstrate that at half of a wavelength, the psi should equal 1 plus 0I. 3/4 of a wavelength, it would equal 0 again. And then at a full wavelength, we would be back to -1. And so on. So we just need to plot the blue dots here and so on. Now, if you look at those two waves, it makes it look like they're just exactly out of phase with each other. Remember that we're looking at the same wave with the snapshot of time, right? So in red is the wave at time equals 0. In blue is the wave after pi over omega seconds have lapsed. But you can see that the effect of omega and the effect of the I is to make it so that the wave can move with time, all right? What we would be imagining is at time equals 0, we have the red wave, and then in blue is the wave as time increases and it's moving in space. So this describes basically a sine or cosine wave oscillating, varying in space and varying in time. Okay, so hopefully I've demonstrated to you that the wave function is defined here is the equation simply for a regular sine or cosine wave that varies in space and in time. And of course, as time increased further beyond pi over omega seconds, the wave would continue to move like that. Okay, so I hope that's useful to you. In the next short video, I will talk about the kind of information that you can get out of wave functions, and we'll talk briefly about operators.